Okay. Okay. So welcome back. Hi. So I hope. Oh wait, it's actually fairly loud. So can people on Zoom hear me? Okay. Thanks. Okay. So yeah, welcome back. So yeah, I was saying to Claudia, I guess today is Factorization Homology Day. Yeah. So I'm changing the original plan a little bit because it's probably time to get to the good stuff. But oh my God, it's actually really loud. So so before that, maybe I should sort of um, tell you a little bit, like make some sort of break and see where we at, because I've done a lot of like slightly combinatorial stuff that seem to depend on a lot of choice, and I sort of want to make clear what does depend on the choices and what doesn't. So first of all, the definition of the character variety itself is like completely canonical. It depends really only on the surface. And the definition of the Poisson structure as well. Like this Goldman bracket, you actually don't need the skein relation to use it. Like you have this formula, which is completely topological. And the skein relation might be useful if you want to sort of compute things. And then I sort of like chose a particular skein relation because I wanted to make a point that it's possible to find some like finite set of relations that sort of generate all the others. But of course, you can choose like not to do that, and you can take all relations basically. So if you don't want to make a choice, basically there are like two very similar ideas that are very common in math and I guess in physics. You can sort of average over all choices, so you can just like take all of the choices. And the same goes for the skein category. So I actually use the skein relation to define the skein category just because it was easier. But there is a version where you just don't do that. Again, instead of like picking a specific skein relation, you can just say, okay, I take like tangles in my surface and then I mod out by all relations that exist in RUBG, whatever they are. And this thing is completely canonical. And then there was all this business with, like skeleton and this Fock-Rossley construction. And I really, again, want to make a point that I'm not saying, okay, this was crap, let's do something else entirely. What I'm going to do is really like a version of that where, again, you sort of take all the choices at once rather than picking a specific one. And so in particular, I told you that somehow the main flaw of the skein algebra is that it doesn't glue correctly. Because, for example, if you just take a simple example like that, and you want to sort of cut your surface in two, well, then this guy cannot be obtained either a loop on the left-hand side or a loop on the right-hand side. You need, for this to make sense, you need to be able to talk about stuff like that. And those guys will typically be, morphism in the skein category, but they don't belong to like the skein algebra of the disk, which obviously is trivial. So really, I guess the point I'm making is that you should think of the skein category. I'm saying things slowly because maybe it's a bit dense, but you should think of it as a way of sort of packing together all the representation varieties for all possible finite set of base points at once. So if you want to compute, you can like choose particular base point, you can do stuff with that. And this Fock-Rossley construction tells you that you can compute the Poisson bracket and that it glues correctly. And basically, if you don't want to choose a specific set of base points, just take all of them, and that's basically what the skein category is. So the skein category glues correctly for surfaces, but somehow it doesn't give you like the correct category from a, I don't know, like geometric or representation theoretic perspective. So as I try to outline, basically, if you start with RUBG, it's a category of modules, or maybe a category of sheaves over something geometric. The skein category is not that. Like if you start with a category of modules, you would like the skein category to be also a category of module, but in that case, it's like the category of free modules, or maybe like projective, finitely generated modules, or something like that. So it's not it's not really the good category you want if you want to connect to other things. So that's why I said that it was actually better to think about this category of sheaves on the character variety. But again, it's not like an entirely different object. It's actually generated in some sense by the scan category. And it also has somehow like this topological flavor in it. So in particular, the category of sheaves on the character variety also glue correctly, like you have gluing formulas over surfaces. And I didn't tell you how this works because basically factorization homology will be precisely that on more somehow. And then I told you that all of that can be done with, in a way which is compatible with the Poisson structure, but again without making any choice. And I also didn't tell you how to do that, but I encourage you to read this very nice paper by Pavel Safronov where he explained all of that, because unfortunately it used a bit of like fairly technical machinery, so I didn't want to get too much into that. But basically somehow the upshot is that there is a notion of a scan category for basically any braided monoidal category that again is completely canonical, doesn't depend on any choice. But again, it doesn't really give you like the sort of correct answer. And the claim is that factorization homology, in that particular case, you should really think of it as some slightly fancier version of this Keynes theoretical approach that actually gives you the correct category. Like basically it's a version that gives you some sort of like completion of the scan category on the node. And I guess this is it. So basically the plan is, well, try to find a way to replace rubG by rubQG, which is the representation category of the quantum group associated to G. So according to Claudia's survey, half of you don't know what that is. So I will explain this eventually, but not just yet. Because this is one of these examples where actually I care about this example, but it's actually easier to do this more generally, like for arbitrary braided monoidal categories, and then sort of this will be an example of this computation. And yeah, I don't know if some of you care about that. I should also say that one of the drawbacks of the scan category is that it doesn't really, what I was saying is that you can take the scan category and somehow like take some sort of completion and you would get factorization homology. That sort of works only in the semi-simple case. So those categories are semi-simple, meaning that every object is a direct sum of simple objects. But some people, looking at you, they care a lot about non-semi-simple categories, and that series sort of doesn't really work, but factorization homology does. So that's another sort of nice thing. So I guess that's it for the sort of recap. So yeah, so basically I want to run some particular example of factorization homology, but to do that I have to tell you which targets I want to use. So we are going to start doing a little bit of abstract, not so abstract, category theory. So I guess this is it part 3? Yeah, probably. Like something I want to call categorified linear algebra. Well, basically I want to take like linear categories, and you should think of this as some sort of like categorified vector spaces. And I actually need some very specific example of categories. And the reason for that is at the end of the day, so remember that this category I defined as basically possibly infinite direct sums of finite dimensional modules. And the reason I need possibly infinite direct sum is because I want, like the algebra function of the representation variety to be there. And this is infinite dimensional. So I can't just take like finite dimensional modules. So you get something which is a bit scary, like the collection of objects in there is not a set, which I'm not sure I know what to do about that. But the upshot is that you need some example of like large categories. But because you want to do linear algebra, you still need something like some sort of basis for those which you can sort of, they are large category, but you can still like control what's going on basically. So yeah, so let me start with a few definitions. So I should say that from now on, every well, not from on, it already was the case, but every category I consider is C-linear, which means that the home spaces are actually vector spaces, but there might be infinite dimensional vector spaces, but they are vector spaces, and everything is linear, basically. Okay. So, so definition. So maybe let's see. Be a category, and again, I mean linear category. Recall that. So let X be an object in this category, and we say that X is called compact if out of X commutes with or preserves filtered colimits. So if you're not familiar with that, like I am, you should think of this as, for example, like infinite direct sums are. I mean, finite direct sums are filtered colimits, but that's not the hard part. Like infinite direct sums are filtered colimits. And we say that X is projective if this functor actually preserves finite colimits. So again, if you don't really know what that is, you should think about it as basically quotients. And the sort of nice thing that happens if you are in the linear setting, I don't think that's true otherwise, is that basically every, like an arbitrary colimit, or I should say a small colimit, like a colimit indexed by a set, is somehow made up of filtered and finite colimits. So if you have both of them, then you have all of them. And so I want to say that X is tiny. Many people also use the word like compact projective if out of X commutes with arbitrary like small colimits. Okay. And so just to, it's probably a little bit abstract, but to give an example, if A is an algebra, possibly infinite dimensional, and C is a module, then basically compact means finitely generated. Projective means projective, and tiny means finitely generated projective. Okay. So that's the basic intuition you should have in mind. And so in particular, in the category of modules, I don't like free, finitely generated free modules are tiny. And of course, it's well known that every module is a quotient of a free, finitely generated free module. And a colimit of those, sorry. So the idea is that in this particular example, those tiny objects actually generate everything under colimits. And so this gives us a definition. So definition C is called locally finitely presentable if there exists, sorry, actually, I forgot something. If there are like two conditions. If it has all small colimits, and if it is like if every object is a colimit of compact object. So let me pause for a second. So really, as I said, the idea is that the fact that it has all small colimits tells you that it's a large category. Like you can take, I don't know, a direct sum of 1021 copies of an object, and this will be in there. So this is really huge. But then the second condition tells you that there is something like a basis. Like this, you can choose a set, and this will actually be a set of compact objects, such that somehow every other object can be written as some sort of linear combination, or in that case, like colimit of those objects. So it means that it's not too big, and you can really will sort of work with this basis to do stuff. And then there is another definition for the other notion is called locally tiny. I don't think this is a standard terminology, but well, let's invent it. If it also has all small colimit, and if every object is a colimit of tiny object. Okay. So again, let me give you some example. So typically, L mod for algebra is always locally tiny. And as a set of generator, you can just take, basically you can take 8 self. Or you can take all 3 modules of finite rank, or you can take all projective modules of finite rank. So the choice is not unique, basically. But somehow there is like a maximal one. And now if C is a coalgebra, then C commod is always locally finitely presentable. Where as a set of generator, you can take the finite dimensional comodules. And here I really mean like finite dimensional as vector spaces. And the thing is that it's not locally tiny in general, because it's sort of well known that the category of comodules of our coalgebra might not have like an house projective object, if you know what I mean. But sometimes it is. So there are, I think they are called something like left semi-perfect or something like that. But for example, if you take O of G, comodules, which is exactly rep G, that's another definition. This one is actually locally tiny. Basically because it's semi-simple, so in that case, that works. No, it's any small colimit. Sorry, here it's filtered. Yeah, you're right. And here it's just arbitrary. Yeah, thanks. And so in particular, I can define my target category. So let S be the 2-1 category whose objects are, let's say, maybe I should give it a better name. I don't know. Well, no, I think that, I don't know. Let's just call it LFP. That's a good name. So let LFP be the 2-1 category where objects are locally finitely presentable categories. And morphisms are linear colimit preserving functors. Okay. So basically, I have this nice compatibility with, I mean, those categories are generated under colimit by some set of objects. So I want functors to preserve that. Okay. And I actually think I might need a variant of that. So let LFP C be the same category, but where you ask functors to preserve compact object. So I can ask the functor to just be compatible with colimit and be linear. And then I can ask functor to be linear to preserve colimit, and I want them to map a compact object to a compact object, basically. So this is a full subcategory of this one, obviously. And you sort of have a nice categories characterization. So this is, I don't remember if like the special one. So it's one version of something called the adjoint functor theorem.
So in LFPC, the functors also preserve colimits?
Yeah. It's an extra condition there. They preserve colimits, they are linear, and in addition, I want them to preserve compact object, which is why, again, this is like a full subcategory of here. Oh, sorry, and I should say, I want two morphisms in both cases to be natural isomorphism. Not all natural transformation, but just natural isomorphism. That's why it's a 2-1 category, because two morphisms are invertible. And so there is various version of something called the adjoint functor theorem that tells you that a functor in LFP, sorry, I'm not sure it's lack of, sorry. An arbitrary linear functor between two LFP categories is actually a morphism in this category, so it's colimit preserving if and only if it has a right adjoint. So basically, another way of defining this category is to say objects are locally finitely presentable category, and functors are left adjoint of arbitrary functor. And that's one point. And again, assuming that you preserve colimit, if in addition it preserves compact object, if and only if that right adjoint preserve filtered colimits. So somehow you know that there is like a general pattern in this kind of thing, like the compact object are those whose ohms out of this object preserve filtered colimits, and the functor preserve compact object if the adjoint preserve filtered colimits. So there is this kind of symmetry. And so a nice feature of this category, which is a requirement if I want to run factorization homology, is that it has a natural like linear tensor product. So this is called the Döhling-Kelly. Or at least we call it that. I'm not sure this is standard either. Tensor product. So let C D in LFP or in LFPC. This actually works for both, which is, I guess, not entirely obvious that this is the same, but anyway. Yeah, maybe it should be a problem. For now, it's a definition. Then the tensor product C, and I will denote it by a square box like this with a cross. C D is an LFP category. Again, C. Now, universal for the following. So basically, this is kind of like the obvious analog of the definition of tensor product of vector space. You want like bilinear functors out of the product to be the same as just functors out of the tensor product. So I want to say something like bilinear. I'm not sure how to say on an equivalence between bilinear functors which are colimit preserving in each variable from C cross D to some target category E, and I want this to be like naturally equivalent as a category, as a groupoid, I guess, to just homes in that category from C box D to E. Okay. Sure. I mean linear in each variable. Is colimit preserve? I'm not sure that colimit preserving imply linear. Oh, maybe it does. Yeah, I guess it does. Maybe not always. Maybe in that case it does, because I think in that case the linear structure is really saying that you can tensor any object with a vector space, which is just taking a possibly infinite direct sum, which particularize the colimit. I guess so. Yeah. So yeah, maybe this is extra. Yeah. I guess I put it just because I want to make the point that it's something like the linear tensor product, and the fact that I want things to be colimit preserving on both sides of course important, but somehow that's not the main point here. So I have this very similar definition to what happened for vector space. And now I should tell you that this actually exists. Yeah, which is good, of course. I suppose. So yeah, so we have a tensor product, and together with that we get that LFP, maybe C, with this tensor product is actually a symmetric monoid. To one category. And I don't know if I will need that at some point, but maybe I will say it again. It's actually what's called a closed symmetric monoidal category, in the sense of the category of, like the home from an LFP category to another is itself an LFP category. And again, I will write it if I need it. I'm not sure I will, but all the things that you can think about work. Like there is something like the home tensor adjunction, and yeah, stuff like that. And just to give a concrete example, which is kind of a motivation, like if that weren't true, then that would be a bad definition. That if you take the tensor product of A mod on B mod, then I guess you can guess what I will put here. Yeah, it's A tensor B mod. So this really generalizes, and in particular, this means that you have a functors from the category of from the category of algebras on bimodules, and I think Claudia will also talk about at some point, to this category, which send an algebra to its category of module, a bimodule to the functor of tensoring with that bimodule, and this functor is in fact symmetric monoidal. That's kind of the point. And it's also fully faithful, which is slightly harder to see. But we will need something like that. This will be an exercise, I think. Anyway. Yeah.
Sorry,
Yeah.
Can you say something about what a symmetric monoidal 2-1 category is?
You mean did I define that?
Like, I mean, just like, what are there any like issues that we need to worry about in it being a 2-1 category rather than a category?
I hope not.
Like symmetric monoidal bi-categories are very complicated, but I mean, this is a strict 2 category, I guess. But
yeah, I mean, I don't have a precise statement, but I think this is an easy one. Yeah, sorry, that's not a real, I don't know much about like symmetric monoidal bi-categories, to be honest. But in that case, the symmetric structure is like, I want to say like the obvious one, things just work out well. But I guess if we wanted to be precise, then we would have to rely on the kind of formalism that Claudia used on so that's her mind. Sorry. Yeah, I must confess we actually do that a lot in the paper. We sort of like compute things on define and say, well, this is a 4 category. Nobody know what it is, but those people have no definition of that. So don't look at us, look at them. Yeah. Sure. So the question is whether somehow this property, basically you're asking whether this characterizes tensor product. I think so. Yeah, I think so. I mean, I guess it would be very hard to come up with a tensor product that satisfies that, and it's not the same as one. So it's not really an answer, but I don't know if there is a formal statement, like if like, is that true that any locally presentable category somehow can be built up out of category of module? I think that there might be something like that. Yeah. Yeah, I guess so. Anyway. Okay. So in particular, because I have this symmetric monoidal category, I can look at algebras on E2 algebras that were just defined in there. So I assume many of you are familiar with the notion of monoidal category, but for me, I want to make this definition. Like a monoidal category so this is not the real definition of a monoidal category. This is like for the purpose of this talk. Of this lecture, I guess. So I guess now that we have this definition, a sort of slick way of defining it is that in E1 algebra, in this category. Okay. So if you unpack the definition, what it means that it is a monoidal category the usual sense. But basically, the only thing I want is that I want the multiplication as a constant product, let's say monoidal category A. But I want multiplication to be a morphism in that category from this tensor product to A. So it's really just a monoidal category in the usual sense, but I just want like the structure map to be actually compatible with this I mean, to be actually a map in this symmetric monoidal category. And I want the tensor product to actually, the multiplication, sorry, of A to be a map out of that and not just of out of the direct products. So again, to unpack, this is a monoidal category where the multiplication is colimit preserving in each variable on linear. And yeah, that's it basically. So then we have another definition, a braid monoidal category. Again, for the purpose of this talk, is an E2 algebra in LFP. Okay. And so again, this is really just a braided monoidal category in the usual sense. Such that the underlying monoidal category is actually satisfies this. Okay. So this is just a monoidal category in that sense, together with the braiding, and there is no extra condition, basically. Yes? So you're asking whether there is like a colimit. I mean, I don't mean that this definition should be changed, but in terms of interpreting it as like an ordinary braided monoidal category. I would have thought that along with this condition, you also need to say like the braiding, right, which tensor A tensor B tensor A. Yeah. Well, I hope the question will be clear from my answer. Like the braiding is a morphism; it's not a functor. So it doesn't really make sense to ask for it to preserve colimits. I mean, the braiding is a natural transformation between one functor, which is the tensor product, and one other functor, which is the opposite tensor product. And the braiding is a natural isomorphism between those. So I don't see what condition you could ask for. Conquers with the values in LFP, no? Say again? Sorry, I'm probably being confused. I'm probably just being confused. So should I go now? Yeah. Yeah, no problem. So how I'm doing about time? So I'm phrasing things this way, obviously, because I want to, run factorization homology with this guy. So let me give you a sort of baby version of what Claudia just said. So I will, probably repeat stuff, but that's probably good things, since this is supposed to be the main topic of this lecture. So I sort of forgot to put like subsections, so let's, So it's a bit of a lie because I won't do factorization homology at the same level of generality as Claudia. So just a very particular example. Somehow it's like, I mean, there are like two directions. So it's probably like one of the first non-trivial example. So let's LCD2, so for me n equal 2, be the 2-1 category. With objects are, probably I should put an or here, but I don't want to have it always with me because I will always consider only that. So objects are oriented, basically surfaces, maybe with boundary. And basically the space, like the groupoid, I should say that like home in that category from n to n is basically the fundamental one groupoid of the space of embeddings from n into n, like oriented embeddings. Okay. So to unpack what I want to say again? Yeah, sorry, capital N. Yeah. So basically what I mean is that one morphisms are embeddings from M into M, oriented embedding. And then two morphisms are like isotopies between those. Okay. So basically this is like this is some sort of like truncation of the n equal 2 version of the categories that Claudia defined. And inside there, I have this category of disk. It's a full subcategory with objects are finite disjoint union. Of disks, or copy of R2. And as we saw, both are symmetric monoidal. With respect to disjoint union. And I don't know why I'm thinking about that now, but I just realized that for the previous section, I didn't give you references, so let me just write that here. So reference for LFP. I've put two in the list. I think one is Ignacio Franco, Lopez Franco, sorry. And then there is Brandenburg, Shervasitu, Johnson Fred. And again, this is Johnson Fred, just one person. I guess many of you know him, but they're like two sort of, I mean, those both papers have like new results, but they have like a good expository part about locally presentable category. So sorry, that was just a side note. Okay. Yeah, I will do that in a minute. Yeah, I don't want to mix both. Yeah. Okay. So basically, the claim is that a symmetric monoidal functor from this category of disks to LFP, disk 2, is the same as something called, let me put in parentheses because I don't want to care too much about that, a balanced braided monoidal category. Yeah, but I said I wouldn't put it here because I will only consider our LTD. That's why I put parentheses around it, yeah. Okay. So indeed, as Luca is pointing out, if I were taking the version for like framed manifold and framed embedding, then this would literally be a braided monoidal category. But because I want oriented things, I need something called a balanced braided monoidal category, which is a braided monoidal category with an extra automorphism of the identity functor, which satisfies some axiom. And I don't want to say this axiom, but in particular, ribbon categories, are balanced in that sense. And basically, that's the main example I care about, so that's fine. And well, how does this work? Well, I hope I'm not spoiling Claudia's exercise, but tell me if you don't want me to do that. But so basically, the idea that to a single disk, you attach A as an object. Okay. Yeah. And then if I have like two disks, which I embed into a larger one, in a specific way. So this is a morphism in my category, so I should get a functor from A box A. And why this is A box A? Well, because my functor is symmetric monoidal, so it sends the disjoint union to the tensor product. And so it should give me a functor from here to here, and this is just T, the multiplication, like the tensor product in A. Then, because I have two dimensions available, I can swap those two guys around like this. And of course, this will go to breaking. And again, if you're wondering, I can also take a guy like this and make him do a sort of full rotation, and this will go to Caesar, which is a balancing, or the ribbon element, if you rather. Okay, so this is, in graphical terms, this will be like this. Yeah, this is a sort of Log-Small wreath in the category. So long story short, ribbon categories have something to do with framed tangle. And because the framing, this thing is not equivalent to just a straight line. There is some twist appearing, and this twist is precisely that here. Okay. Mm-hmm. No, objects are surfaces. Oh, you mean in this? Yeah, objects are. Yeah, all embeddings. Yeah. Yeah, exactly. Yeah, like homotopy classes of path. Yeah. That's a good question. Yeah, yeah, it's. Yeah, no, but I mean, I guess in a way you can sort of strictify and ask like basically. Yeah, I mean, I think it's kind of the same sort of issue as when you basically what I'm doing is that I'm instead of taking the whole groupoid fundamental groupoid, I'm actually choosing specific uh, something like an opera of base points in there, like a collection like for I choose a base point for every n. So this is a functor in this is a morphism in LFP. So this is a there's a category of morphism. Yeah, exactly. There is a groupoid of morphisms indeed. So I guess yeah, that's a very good question actually. I think that's sort of a subtle point. So the thing I'm doing is that I'm basically instead of taking the full groupoid of embeddings, I'm choosing like a specific collection of base points for every n, which are sort of compatible with the inclusion that I have chosen. And then I know abstractly that this is equivalent to the full groupoid, but of course the inverse equivalent is like some non-canonical. There is no explicit way of. Yeah, I mean, again, there is something like you can look at something like I don't know, like the braid groupoid, if you want, Re with respect to like arbitrary configuration, or you can restrict to a particular set of configuration in there. And those two things are equivalent, but of course, there is one obvious map in one direction, and the inverse equivalent is something that you can't really write down, but this is there. Like this is, this general, I mean, that of course, the general fact, if I take the fundamental groupoid with respect to certain base points, this is actually equivalent to the whole groupoid. But basically, to construct the inverse equivalence, I have to choose a path between every point on my base point. So this is like the same, this is the same phenomena, basically. Yeah, I mean, okay, but maybe I should say like a symmetric monoidal functor is like abstractly isomorphic to something like that. Yeah, yeah, yeah. I guess even yeah, yeah. I guess if I wanted to be like the sort of fancy version is that this thing should be something like a factorizational algebra with value in over R2 with value in categories, and then there is a theorem that this is equivalent to Braid monoidal category, but this equivalence is like there is a smaller thing embedding into a much larger thing, which happens to be an equivalence, and the inverse equivalent is just not explicit, basically. So maybe I should say it the other way, like if I have a Braid monoidal category, then this gives me a functor like this. I don't know if that's better. But yeah, yeah, sure. No, you're right. Yeah, that doesn't solve the problem at all. So that's that was a bad thing. Yeah. But you're right that there is like no. I actually was very very confused by that for a little while. So I understand the frustration, but
Maybe you can share with us.
sorry. Yeah. So basically, Natalie was making the point that in this category, I choose like my morphisms are all embeddings. So if I want to define a functor, I should tell you what happened for like every possible embedding of two disks into a larger one. And I'm actually not doing that. And the reason why is that in fact secretly in my disk category, I'm replacing the space of all embeddings. The fundamental groupoid of the space of all embeddings, which in the case of disk, as Natalie says, are basically configuration spaces. So this is basically like Braid groupoid or something like that. And I'm actually choosing like a specific set of base points in this groupoid. And I'm defining the morphism only for like certain particular embeddings that I've chosen. And of course, this is equivalent, but in a sort of fairly abstract way. Yeah.
I just wanted to add that actually this point is written down in great detail in this textbook by Benoit Fraisse. I mean, he really defines
Yeah.
combinatorially this great operand, and then proves that there is a map, not necessarily a canonical one, but a map from this great operand into two, and this is then an equivalent.
Indeed. So look.
So this choices.
So Lucas is pointing out that there is this big book by Benoit Fraisse, which explains this in great details, basically, where he shows the equivalence of this, what's called the parenthesized Bread operad, which is like the Bread groupoid with respect to a very specific set of base points, which is compatible with the operatic structure, on the full Bread operad, basically. Yes, that's a fair point, Frank. A good point, Frank. Okay. So, how are we doing? Okay. Okay. So now I want to state a theorem. I think. No, I think I give the Ayala Francis, not the Ayala Francis Tanaka. So, yeah. So these are the references I have for that, Claudia. The reference I have for factorization homology, Ayala Francis and Lurie. Do you want me to add anything? Okay. Yeah, I'll add it to the list at some point. Yeah, I'm not sure I knew about those notes, but yeah. So,
What's the name?
sorry? It's Hiro Tanaka.
With co-authors in particular Lucas Luno.
Oh, my bad. Apologies for that. I will put the correct reference on the list. So, okay, so basically we have, so if we have a balanced Bread monoidal category, that gives me a symmetric monoidal functor from this category of oriented disk to FP. And this thing embed into category of surfaces. And the theorem is that, sorry, so let's say A here. So there exists a canonical extension. So Claudia already told you this is a canonical extension, but I don't want to say that. Which is symmetric monoidal. And satisfies and characterized by, this is a very odd sentence, characterized by excision. So what is that? So this is the end of the talk, so I will need to introduce more material to define that, but basically this thing is what encodes the compatibility with gluing. Okay. So basically this is a sort of, morally this is saying that this, and it's called factorization homology, but you knew that already. So basically what this theorem is saying that we can construct this invariant of surfaces, and saying that it satisfies excision is morally saying that this is a TFT, but going from there to the fact that it's a TFT is a highly non-trivial task, but that's sort of the central idea of like why it's actually a TFT. So this is a version of compatibility with gluing, which is very close in spirit to what happened for TFT, but it's actually non-trivial to get an actual TFT from there. But I will only sort of need this excision property. So basically a TFT in general tells you that there is like some compatibility with gluing. And the sort of whole idea here is that in the particular case where this construction comes from factorization homology, this compatibility with gluing is actually as simple as it can get. Like there is a very nice algebraic formula that tells you what happened. And I guess this will be the topic of the next lecture. So thank you. Okay. So are there any questions? Comments? Yeah? No, it's a natural transformation between functors in LFP. This is a natural, like there is one functor which is the tensor product of the category, so it's a functor in LFP from A box A to A. And then there is the opposite multiplication, which is also a functor in LFP from A box A to A. Yeah, the braiding is like the image of this sort of this path in the space of embedding by this functor, but it's not itself a functor from. Okay. So for people on Zoom, this was another version of the question of whether the braiding had to somehow be compatible with colimit. On the answer is no. There's no such thing. Sorry, if that's like shorter version of. Okay. 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 Well, so I guess let's have lunch.
And